Okay, talking about our periodic trends, now that we understand a little bit more about what's taking place and why the periodic trends are the way they are, we can look at what the trends are on our periodic table. And then at the end, you will want to fill out some little mini periodic table to look at that shows you what these trends are so you can find quickly like which one has a higher ionization energy or which one has a lower ionization energy. So first we have your atomic radius. Since the cloud's edge, where the electrons are at the end, is difficult to define, what scientists actually use instead of the actual atomic radius and measuring, remember radius is from center to outside of a circle, instead of doing that, they actually use a covalent radius. They just take half the distance between the nuclei of two bonded atoms. So they'll see when that atom is bonded to another one of itself, they measure the distance between the nuclei because that's easier for them to locate specifically and find. And then they cut that in half to find the atomic radius. So the same thing you can see here, they're in picometers. That's what they're usually measured in, which is 1 times 10 to the negative 12. So remember, move the decimal place 12 places to the left. Meters, or angstroms, which is that A with the charm kind of looking thing on top. An angstrom is 1 times 10 to the negative 10 meters, so just a little bit bigger of a measurement. But you can see down here, these are our different halogens, and then hydrogen and oxygen, nitrogen. They take the distance between those two bonded together, and then cut that in the nuclei to nuclei distance, and cut that in half to find the atomic radius. So it's not actually a specific radius. The actual radius of the element is probably a touch bigger because when you have two elements bonded together, they kind of get squished together. But that gives us an idea and a reference to base off of them that's equal for all of them. So the same reference to measure the atomic radius. Know what these variables are for your test because they're also listed on your mini periodic table that you'll get at the end because you will want to know what the variables are that measure these different things. So the trend for the atomic radius, the atoms get larger as you go down energy levels, as you go down the group because there's more energy levels. So if you remember Bohr's model, the further you have a nucleus, n equals 1 right outside your nucleus, n equals 2 will be a little bit further out, n equals 3 a little bit further out, 4, so on. So the more energy levels you have, which is, remember, that's what your periods are equal to, is the number of energy levels. So as you go down your periodic table 1 through 7, you're putting pretty much more rings around the outside. So that's why they get bigger, the elements get bigger as you go down the group. As you go across a period, which is from left to right, the atoms are getting smaller. So because of this, is because they have increased nuclear charge, and they don't have additional shielding. So there's no extra electrons between the inside electrons and the outside electrons. So there's no extra shielding, but you have more protons. As you go one step left to right, you gain a proton each time. So you're gaining those protons. They're going to want to pull those electrons in closer and closer and closer. So the more protons you have, they're going to pull them in closer, and you're not gaining any shielding because the electrons that are being added to the outermost shell. So the ones in between they're not going to be, your furthest away electrons are still going to be the same distance away until you have an extra proton that's going to pull them in tighter. So each step does add a proton and an electron, and then around 1 or 2 neutrons. The electrons are added to the existing energy levels or sublevels, so the effect is that there's more positive nucleus, and the electrons are the same. As you add more electrons, they're the same distance away. There's a greater pull towards the center, that makes the atom smaller. The largest atom that we know of is cesium, or Cs. There might be more below it. We just don't know their radius yet. You never know of that. But atoms do get bigger as you go down a group because they have more energy levels, more shells, more orbits around the nucleus, but they get smaller as you go left to right because there's more protons to pull those electrons in tighter. Think of the Coulombic attraction references that we did last time. Then we have ionization energy. That's just the energy required to remove an electron from an atom. It's measured in kilojoules, or kJ is the symbol for kilojoules. The larger the atom is, the easier it is to remove its electron. Larger atoms have a weaker nuclear charge, holding the outer electrons, thus they have lower ionization energy. Remember, ions are something that has a charge, they've gained or lost electrons, so it makes sense that ionization energy talks about how easy it is to move an electron from an atom. So if they have a higher ionization energy, it's harder to remove the electron. the lower their ionization energy, it's a lot easier to remove the electron from them. And then the bigger they get, they have less effective nuclear charge. They can't pull on those faraway electrons very well, so those electrons are easy to plop right off. So your ionization energy and your atomic radius are inversely proportional. As your atomic radius gets bigger, your ionization energy goes down because it gets way easier to pull those electrons off the outside. The trend for ionization energy, as you go down a group, ionization energy decreases because they're getting bigger as you go down a group, so it's easier to remove the electron the further it is away from the nucleus. So as we're going down the group, they're getting bigger. Those further out electrons are easy to plop off because they're a long ways from the nucleus, long ways from home. It's a lot easier to stray them off the path and take them away. As you go across a period left to right, your ionization energy increases. It becomes harder to remove an electron because the electrons are pulled closer to the nucleus as you move across a group. So if you remember the atomic radius, they're getting smaller as you go left to right. So as you go left to right for ionization energy, they're getting smaller, so it's harder to pull them away. Noble gases have the highest ionization energy by quite a ways because they are stable with their full set of valence electrons. They do not want to get rid of them because they are perfectly happy and stable home. They don't need anything else. They don't want to lose anything else. They have their 8 valence electrons. It is extremely difficult to pop off an extra electron off of a noble gas because they're already full and they're happy and satisfied with that. So then the ionization energy is extremely high comparative for your noble gases on your far right. At this point, you should stop and complete your periodic table puzzle 3, density and solubility lab, and a crossword.